Welcome to part 4 of our snow science module. In the first two parts of this module, we discussed crystal structure and specifically what parameters drive the formation of crystal, vapor pressure and temperature, and how crystal structure changes, metamorphosis, in the snowpack. We discussed the effects of radiative cooling and heating and the concept of radiation balance and its effect on near-surface facetting. All of these processes contribute to the layered structure we see in the snowpack, and more specifically to the creation of weak layers that could fail and result in an avalanche. But an avalanche doesn't happen until there's a trigger, some event that initiates a failure in a weak layer in the snowpack. In this module, we will explore fracture mechanics. Fracture mechanics are the physical processes that initiate a failure in a weak layer. We will also discuss how this failure propagates in the snowpack. As you may remember from level 1, the key ingredients for a slab avalanche are a consolidated layer, the slab, a weak layer, a slope between 30 and 45 degrees, and lastly, a trigger. But how do these elements result in a slab avalanche? We've all skied on slopes that have these elements and not triggered an avalanche. What's the critical event that starts the avalanche train in motion? Let's look at a trigger event in more detail. Recall from Module 1 that triggers can either be natural events like a cornice failure or man-made events such as a snowmobile. Failure initiation starts with an event that creates damage in the weak layer as shown in the far left on this slide. This is what we would normally consider the trigger event. The damage event drives the formation of the initial crack followed by crack propagation. This is the critical point in the process. The crack propagation can go some distance and then stop, or the crack can propagate in two dimensions, laterally across the slope and up and down the slope, shown as dynamic crack propagation in the slide. This results in the collapse of the entire slab. At some point, the tensile stress on the slab exceeds the energy in the ice lattice and the slab breaks free and slides. So what determines if the initial crack propagates to a slope scale event and slides or stops after a few meters? There have been several models to attempt to explain this. The first we will look at is the slope parallel shear model. In this model, the weak layer collapses in response to a trigger event. The collapse of the weak layer results in a shear force between the consolidated layer and the base layer. If this shear force exceeds the force of friction holding the consolidated layer in place, the fracture propagates. At some point, the mass of the slab creates a tensile fracture that releases the slab and the avalanche happens. Whether the shear force exceeds the force of friction depends on variables like slope angle, thickness of the consolidated layer, and any force concentrating points like rocks or trees. However, there are several problems with the slope parallel shear model. For example, this model does not really explain why the weak layer failure may propagate uphill, nor does it fully explain failure without release, or how wumping occurs. So the anti-crack model was developed to try and explain these phenomena that we see in real avalanches. This slide shows the basics of the anti-crack model. It starts with the collapse of the weak layer, crack formation, shown in the top figure. The elastic properties of the slab then communicates the failure to adjacent areas of the weak layer. This is propagation. As more portions of the weak layer fail, the tensile stress on the slab increases, as you can see in the second figure on this slide. There's a race that occurs between the rate at which the weak layer collapses and the tensile force increases on the slab. If the weak layer collapses faster than the tensile strength can increase on the slab, the failure propagates across and up the slope and we have an avalanche. If the tensile stress increases faster than the weak layer failure can propagate, the tensile failure occurs and the propagation stops. No avalanche. There is a critical crack length that determines who wins the race. the propagating collapse of the weak layer or the tensile failure of the slab. If the crack length exceeds this critical crack length, the collapsing weak layer exceeds the rate of tensile failure, and we have an avalanche. This is a cool picture that's been on the title slide of all the snow science modules, showing weak layer collapse and tensile failure. You can clearly see how propagation stopped when and where the tensile failure occurred. One last topic I'd like to touch on is spatial variability. This is one of the areas where a lot of research is going on in snow science. Many people in the avalanche community have noticed that snowpack stability can vary greatly across a slope. A snow pit in one area may show great stability, while another pit 5 meters away may demonstrate great instability. Why is this? The basic cause and the issue researchers are concerned with is that the slope is not homogeneous. There are many physical variables such as aspect, crystal metamorphosis, water content, to name a few, that affect snowpack stability. Some of these parameters, like aspect ratio, are slope scale, while others, like crystal metamorphosis, occur at the micro level. This is why small variations of distance on the slope can produce such differing results in the snowpack and the ability of a crack to propagate. And this is why when we dig a snow pit, we're looking for signs of instability, not confirmation of stability. This is why so much of the mitigation efforts at resorts are so critically dependent on local knowledge and the slide history of an area. And it's why if you're skiing in an area you're not familiar with, be extra cautious if you're in Avy terrain and conditions are other than rock solid. Which brings us to the end of our snow science module. We've covered a ton of material, and it's pretty complex material at that. So if you need to go back and review some or all of this material, please do that. Thanks for your time, and that's a wrap for now.